Namaskaram. In this session, we will discuss a basis of a vector space. Okay, in last few sessions, we have seen that vector space and span of a given set, and one more thing, linearly independent and dependent. And also, we know that the span of a given set itself a vector space. Okay, okay, let's consider this definition. A subset S of a vector space V is called a spanning set for V if span of S is equal to V. That's all. That means we have a vector space V and this S is a subset, and we know that corresponding to every set we can define span. What is span? Set of whole linear combinations of elements of S. If this span is exactly equal to the full space V, then we can say that this S is a spanning set for V. And we know that in general, this span of S is a subset of V, and span of S is always a vector space. If that span of S is equal to full space V, then we can say that this S is a spanning set. Okay. Okay, before defining the basis, we have to analyze this example. Consider a vector space R square and span of 4 subsets. The first subset S1 is equal to 1, 0 and 0, 1. And what about the span of S1? And we know that by definition of span, it is set of all linear combinations, right? So some A times 1, 0 plus B times 0, 1, where A comma B belongs to R. This is the definition of span. And what is this? This is nothing set of all AB, where A comma B belongs to R. And what is this? This is nothing. This is our R square. Clear? So in this example, S1 is a spanning set. Clear? S1 is a spanning set for R square because the span of this S1 is R square because this contains all the ordered pairs. Okay. Okay, next we have to find span of S2. What is S2? S2 contains 1, 0, 0, 1 and 2, 2. Okay, already we know that span of these two elements is our full space R square. So naturally we expect span of S2 is also R square, right? Anyway, we have to consider the span of S2, that is equal to A times 1, 0 plus B times 0, 1 plus C into 2, 2, where A, B, C are real numbers. That is equal to A plus 2C comma B plus 2C, right? First coordinate is A plus 2C and second coordinate is B plus 2C. And what about this A plus 2C? Here it is clear that A and C both are arbitrary numbers. So A plus 2C is also an arbitrary. Clear? And similarly, here B and C are arbitrary. So B plus 2C also an arbitrary. So what is this? This is exactly our R square. Or you can explain this concept in another manner. We know that R square equal to span of S1. That is our first case. Okay, R square equal to span of S1. And it is clear that S1 is a subset of S2. So span of S1 is also subset of span of S2 because this contains set of all possible linear combinations. If you choose C as 0, this span of S2 is if C equal to 0, then the span is gives exactly a span of S1. So we have extra one more term. So it is clear that this is subset of span of S2. And what about this side? We know that if S is a subset of a vector space, then span of S is always a subspace of V. Okay, we know that if S is a subset of a vector space V, then span of S is always a subspace of V. So it is clear that here our S2 is a subset of R2. So span of S2 is a subspace of R square. So what happened? Span of S2, R square is a superset and subset of S2. So what is our conclusion? That means R square is a subset of span of S2, subset of R square. That means span of S2 equal to R square. Clear? So anyway, we can now we can easily show that span of S2 is also R square. So S2 also a spanning set of R2. Okay, next we consider S3. S3 is 1, 1 and 2, 2. Okay, this is also a subset of R2. Then what about span of S3? Set of 4 linear combinations, that is A into 1, 1 plus B into 2, 2, where A and B are arbitrary. This become A plus 2B comma A plus 2B. So what is span of S3? Geometrically, what is this? Yes, here it's whatever be the x coordinate, that is same as our y coordinate. So this is nothing. Geometrically, this is y is equal to x. Clear? We know that y is equal to x is nothing. It's a line like this. This is our y is equal to x. So this is our entire R2 plane. In this entire R2 plane, span of S3 is not equal to R2. Span of S3 equal to this straight line y is equal to x. So S3 is not a spanning set of R2. S3 is not a spanning set of R2. Okay. Okay, next we consider S4. S4 equal to 1, 1, comma 1, 0. And S4 also a subset of R2. And what about the span of S4? Yes, by definition, span of S4 equal to A into 1, 1 plus B into 1, 0, where A and B belongs to real numbers. So this is equal to set of whole A plus B comma A, where A, B belongs to R. And what about this one? Yes, here A is an arbitrary, that means A can take any value. Then A plus B also take any value, because this B does not involve in this coordinate. So B is an arbitrary. So B plus A also another, it's like a new arbitrary. Okay. So this A is arbitrary and B is arbitrary. So we can treat B plus C is a arbitrary with respect to A. Okay. So anyway, this is nothing R square. For example, you consider the element 5 minus 1. If you choose A equal to minus 1, what is B? Our aim is to make this A plus B equal to 5. Yes, if you choose A equal to minus 1, then what about B? B equal to 6. Right, if you choose B equal to 6, B equal to 6, then 6 plus minus 1, that is equal to 5. Okay, so we can treat A is arbitrary. Similarly, A plus B is also an arbitrary, because this involves an arbitrary B that isn't involved in the second coordinate. Okay, that's why this is R square. Anyway, this S1, S2 and S4, these three sets are spanning sets of R square. That means we can generate our entire R square. We can generate R square using S1, S2 and S4. Span of S3 is not equal to R square. Okay, so this is not useful for representing R square. That means we can represent R square using these three sets, because you can generate any element. You can generate any element R square using the elements of S1 or elements of S2 or elements of S4 by taking the linear combinations. Okay. That's why I'm saying these three sets are representative of R square. Then there is a natural question. Out of these three representations, because these three sets represents same vector space. So the natural question is, out of these three sets, which ones are best? Which is the best one? Best one means with respect to the size of the set, because we can generate entire R square using S1, S2 and S4. So S2 contains 3 elements. S1 and S4 contains only 2 elements. So out of these 3, these two, comparatively these two are best. Right? Best in the sense that with respect to their size. Okay. Then how to ensure this minimality? Suppose there exists another set. Suppose there exists another set contains only one element which spans R2. Then this is the best one out of these three. Correct. So how to ensure this minimality of a spanning set? Yes, that is ensured by the concept linearly independent. Okay, linearly independence. Okay, so our aim is to find, suppose we have a vector space V, our aim is to find a best set. A best set. Best in the sense that it is very minimum, such that it spans our V. Right, that's the idea. So our aim is to find a best set B, subset of V, which represents entire V. Represents means it spans V. Best in the sense that it should be minimum. So how to describe this best and span? So that is a concept of basis. So now we are ready to define the definition basis. Okay, span of S means span of S is equal to V means there is a comma, means S is a linear representative, S is a representative of V, and linear independence ensures that the set S contains only minimum number of elements. Okay, because there are different sets which spans the same vector space, and we have to find the minimum, which is the minimum set which spans entire vector space. The minimality is ensured by linear independence. That is the definition of basis. A set V is called a basis for a vector space V if span B equal to V. That means B is a representative of V, because we can generate entire V using the set B. Okay, if it is best only when this B is minimum, B contains only minimum number of elements. That is ensured by the independency, and B is linearly independent. So if B satisfies these two conditions, then we can say that this B is a good representative of V. That is called basis. Clear? So a basis is a spanning set of V, and it should be linearly independent. Okay, now in our previous example, which of the following subsets are basis for R square? It should be a spanning set and independent. And what about S1? We know that its span is R square, and this also R square, and this also R square. This is not equal to R square. This is only our Y is equal to X. Okay, so you can throw out this case. This is not a basis because this is not a spanning set of R square. Out of these three, which are the bases? Yes, we know that 1, 0 and 0, 1. This is a linearly independent set. Why? Because one of them is not a multiple of other. So it is independent. If it is dependent, for a two element set, one of them is a multiple of other. Okay, here one of them is not a multiple of other, scalar multiple of other. So this set is linearly independent. So linearly independent and span equal to R square. So this is a basis for R square. And what about this? Is it independent or dependent? Yes, we know that this set is linearly dependent. Why? One reason is you can write this 2, 2 as a linear combination of remaining vectors. Okay, you can write this 2, 2 as 2 into 1, 0 plus 2 into 0, 1. That which S2 is linearly dependent. Or you can find our scalars C1 into 1, 0 plus C2 into 0, 1 plus C3 into 2, 2 equal to 0, 0. What are the values of non-zero values of C1, C2 and C3? Yes, if we choose C1 as minus 2 and C2 is minus 2 and C3 equal to 1, then this linear combination is equal to 0. Here not all CIs are 0. Anyway, this set is linearly dependent. So this is not a basis. Not a basis, but it is a spanning set. Okay, what about the last one? Yes, you can easily verify that this also linearly independent, because it contains only two vectors and one of them is not a scalar multiple of other. Right? So this is also a basis. So out of these four sets, first one and fourth one, they are basis for R square. And S2 is a spanning set of R square. That means S2 can represent R square, but it is not small. Okay, so this is not a basis. And S3 is not a spanning set of R square, so it is not a basis. Clear? So the another important thing is, for a vector space V, bases are not unique. Maybe different bases are possible. In this example, R square has at least two bases. This S1 and S4, both are bases. Okay, and this is a special basis, and that is called standard basis for R square. We denote E1 by 1, 0 and E2 equal to 0, 1. And this is a special basis, common basis for R square. And this is called standard basis for R square. So similarly, you can define bases for Rn. Then there is a natural question, what is the, or which is the standard basis for Rn? Similarly, you can define E1, E2, etc., En. Then you can generate every element in Rn using this E1, E2, En. What is E1? Yes, even is nothing, 1, 0, etc. 0, and this contain total n elements, say n element vector. And what is E2? Yes, 0, 1, 0, etc. 0, and similarly 0, etc. Last one is 1. So E1, E2, etc. En. You can generate every element in Rn using these n vectors. You take the linear combinations of this E1, E2, En, and this set is called standard basis for Rn. Okay. Normally we choose standard basis as basis for Rn if nothing mentioned. Okay. And next we are going to define finite dimensional. What is finite dimension? A vector space V is said to be finite dimensional if it has a basis containing a finite number of vectors. That's all. Suppose a basis contains only finite number of elements. Finite means it is 1 or 10 or like that. So then we can say that finite dimension. For example, R square is finite dimensional because R square has a basis containing 2 elements. Okay, at least our standard basis. Similarly, Rn is also finite dimensional because Rn has a basis containing E1, E2, etc. En. This is a standard basis of Rn. So Rn is also finite dimensional. Okay, this is our last example, and we know that this S1 and S4 are basis for R square. So another interesting thing is in this example, these two bases contains same number of elements, right? S1 contains 2 elements, S4 also contains 2 elements. This is the another property of basis. This is the result. Every basis for a finite dimensional vector space must contain the same number of elements. Okay, that means if you consider a vector space V, finite dimensional vector space V, suppose B1 and B2 are two bases for V, then this results says that number of elements in B1 must equal to number of elements in B2. Okay, that is true. So every basis for a particular vector space has same number of elements, and that number is defined as dimension. Okay, that is a definition of a dimension. Number of vectors in a basis for a vector space V is called dimension of a vector space and denoted by the dim of V. You got it? So whatever be the basis for a vector space, the elements are always same. Number of elements are always same, and that number is defined as dimension of V. Suppose this is our V, dimension of V. Clear? So this is the definition of dimension. So what about the dimension of R square? So dimension is nothing. It is the number of elements in a basis. And we know that R square has a standard basis. We know that R square has a standard basis like this 1 0, 0 1. This is a basis for R square. And this basis contains only 2 elements. So its dimension is 2. Right. Similarly, what about the dimension of Rn? Yes, it is n because Rn has a standard basis and that basis contains only n elements, so its dimension is n. Okay, this is a simple homework. Find the dimension of Pn. So your job is to first of all find a basis. Basis means the set should be spanning set of Pn and it is linearly independent. Then the number of elements in that basis is the dimension of Pn. Okay. So in a session, we will discuss more problems related to basis and dimension and some properties of basis. Okay, thank you.